Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem, find the kth element of given two sorted arrays. Now the question basically states, you'll be given two sorted arrays, array 1, array 2 of size m and n, and you'll be given an integer k. Your task is to find the element that would be the kth position of the final sorted array. Basically array 1 will be looking something like this, that's a sorted array. Array 2 is a sorted array, and you will be given a value k equal to 5. Now, if you merge them into one final sorted array, it will look something like this, right? And now among this, you need to figure out which is the fifth element. So the fifth element is 6. So that is what you need to print. Now the question has an expected time complexity of log n plus log m and an expected space complexity of log n. But we can still do better, and I'll be solving this in log minimum of n comma n, and we will not be using any extra space whatsoever. I will highly recommend that you should watch my previous video, that is finding the median of two sorted arrays. If you watch that, you will get an idea about how to solve this. If you haven't watched that, it's okay. You can also continue with this video, but it is my recommendation that you should definitely watch that video. Now, let's assume that these are the two given arrays that are given to you. Now, if this question is asked in an interview, what will be the naive solution that you'll tell the interviewer? Now, there can be multiple solutions. You can probably tell them about heap. You can tell them anything. Now, imagine k is given as 5. Why don't I tell them the method that I use while merging in merge sort array? What if I say, let's keep couple of pointers, one over here, one over here. Okay. And while I just pick up this guy, because this is the smaller one, I make my counter to be 1. Okay, I've picked my first guy. After that, I will definitely move my pointer to this guy. Now I compare this guy and this guy, which is the smaller 2. So I'll take 2 and I'll make the counter 2, and then I will increase the pointer to here. Now I'll compare 3 and 3, which is the smaller one. You can definitely pick any one of them. So I'll pick this 3. I'll increase the pointer to over here. I'll increase the counter to 3. Now again a comparison will be done between this 3 and 4. I'll pick this 3. I'll increase the counter to here, and I will increase the counter to 4. Now again the comparison between 4 and 6 will be done. So 4 will be picked. And the moment the counter becomes 5, that means I've picked the 5 elements. And the question clearly stated I require the fifth element of the two sorted arrays. So I can definitely say this element, the last element that has been picked up when the counter becomes 5, is my fifth element of the two sorted arrays. Now what is the time complexity required? Obviously, as you see that, I'll move my pointers just big O of k times. So the time complexity required over here is big O of k, and the space complexity required over here is big O of 1. There's absolutely no need of storing these numbers. The moment you reach this 4, you just print that. Do you need to store this array? No. So the space complexity is big O of 1. Now this is the extreme brute force that you are going to try out. But obviously, when you will tell this to the interviewer, or you'll tell a heap based solution, the interviewer will not be happy with that, and he'll ask you to optimize this. Now if you go through the GFG article, the article that is at GFG, there is a solution of divide and conquer, but that again uses log n plus log m, and the extra space of log n is again used. But I'm going to tell you a binary search solution which will be a much better complexity than what is written at GFG's article. So before moving on to the next part of the video, let me tell you about Coding Ninjas. Now, Coding Ninjas is one of the largest coding education company, and they have taught around 50k plus students. Now, they offer you courses in programming in different languages like C++, Java, Python. They also have courses for machine learning, Android development, data science, and web dev. The content quality is exceptional, as it is made by experts from IIT, Stanford, Amazon, and Facebook. They do offer you 1:1 doubt resolving support, and the average doubt solving time that they take is literally the best in the market. Now, since the courses are really well structured and so many have benefited from it, I guess you should give it a try. And if you feel so, do use the link in the description to avail a discount, which will be added above the one which is already present in the website. So guys, go and check it out. Now, what will be the efficient approach? Now, the first thing that you need to consider is both the arrays are sorted. Now, whenever both the arrays are sorted, which algorithm comes to your mind? Obviously, binary search. So, why don't I try to think of a solution which is related to binary search? Okay, can we think? Yes, we can. Now assume I've been asked to find the fifth largest element or the fifth element in the final sorted array. So how will I find that? Now, if you have seen my previous video, you know how to do this. But let's assume you have not seen that previous video. Then how will you think? Now, can I say, if I am looking for five elements, like the fifth element, and I write all these elements into the final sorted one, it will look something like this. So this is how my final sorted array will look like. Now, if you have seen my previous video, you know what to do. You have to make these five elements. And you know one thing, whenever I call this the left half, let's assume this is the left half. Now, this left half is actually formed by taking some elements, I repeat, it's formed by taking some elements of the first array and by some elements of the second array, correct? For an example, now this is formed by taking 1, 3, 4 from the first array and 2, 3 from the second array. Whereas the right half, right portion is formed from taking 7, 10, 12 from the first array and 6 and 15 from the second array. I definitely know that, correct? Now, if I can figure out how many elements are taken from the first, how many elements are taken from the second, I can actually figure out my answer. What will be the answer? I know that the last element will always be my kth element. Now, this out of these elements, the last element is the largest. So, can I say out of all these elements taken from the first and second, if because this is entirely sorted, and this is also entirely sorted, so can I say if I call this as L1, if I call this as L2, can I say my answer will be max of L1 comma L2, which will be my kth largest element? Yes, I can definitely say that. So now the question boils down to figuring out how many elements shall I pick from the first array and how many elements shall I pick from the second array so that I get this desired. So now the question boils down to actually figuring out how many elements do you need to pick from the first array in the left half, how many elements do you need to pick for the from the second array in the left half. So can I say if I decide I'm going to pick one element, that is the one from the first array, how many will I pick from the second? If there are total is 5, I will be picking something like 2, 3, 6, 15. Correct? So I pick 2, 3, 6, 15. Now if I'm picking 2, 3, 6, 15, can I say the right portion will be having something like 3, 4, 7, 10, 12, and over here there will be nothing. So this is the left portion that I am assuming if I pick 1 from first, 4 from second. Is this the correct one? Obviously not. Because one thing you know for sure, this left arena, I repeat, this left arena should be lesser than all the numbers in the right half. All the numbers in the left are always lesser than all the numbers on the right. Is this the case here? No. So this is practically not possible to pick. So I can say this is not my solution. Can I say what if I will pick couple of elements from this guy and then I'll pick the rest 3 elements because in total the left has 5. So the next 3 elements from here. So the right half will be 4, 7, 10, 12 and 15. Now is this the correct left half? Again, you'll say no, this is not the correct left half, man. Why will you say that? Because this is a 6 and I know all the elements on the left half should be smaller than all the elements on the right half. I already have a 4 which is smaller than 6. So this is obviously not the left half. All the elements on the left should be smaller than all the elements on the right. So this is also not an answer. Now what if I say I'm going to pick 3 elements from the left, from the first, I'm going to pick couple of elements, the remaining couple of elements from the second. So the right half will definitely contain 7, 10, 12 and 6 and 15. Now is this the valid one? And I'll be like, yes, this is the valid one. Now how do you understand that this is a valid one? Because all the numbers on the left, if you carefully observe, are smaller than all the numbers on the right. Hence you said that by picking up 3 elements from the first and 2 elements from the second, I got my correct left half. And if I got my correct left half, I know that the kth element is the largest among the left half. So this is the largest in the first array. This is the largest in the second array. So the answer will be max of 4 comma 3. That's it. This is how you get your kth element in your final sorted array. Now, how do you figure out? How do you figure out if all the elements over here are smaller than all the elements on the right? That's the main point of concern. Now, assume you're taking this as L1. Assume this is L2. Assume this is R1. Assume this is R2. Okay. So, can I surely say this portion will be smaller than this portion because it's the same array? So 1, 3, 4 will always be smaller than 7, 10, 12. So if I can say that this is smaller than this, can I say this entire portion is actually smaller than all these in right? I can. Hence, can I say if L1 is lesser than equal to R2, which will mean that the entire first array, whatever I have picked up, is smaller than the right half. Proved. Now, can I say this is definitely smaller than 615? Definite. So, if I can prove that this is smaller than this, I can also say that this portion that I've picked up is smaller than the right half. Hence, L2, if lesser than equal to R1, that means the entire left half is smaller than the entire right half. Correct? So, I've written my validity condition of left half. Now, the question is, I'll definitely not apply brute force by taking 1 element, 2 element, 3 element. I need a better algorithm because I cannot apply brute force. Why can't we think of a binary search algorithm? What if I say, what is the minimum number of elements that you can pick from this half? You'll be like, I can pick 0 elements, right? And if I say, what is the maximum number of elements that you can pick from this half? You'll be like, I can pick all the elements. Okay, that's fine. So just imagine that you have picked up a couple of elements from the first array, and you have picked up the remaining elements, that is 3 from the second one. So the right half will look something like this: 4, 7, 10, 12, and from here it will be just 15, correct? So this is what you can pick if you pick 2 elements from the array 1. Now, just logically think, if you start to think in the binary search nature, now can I say this 1, 3 is smaller than all the elements on the right? I can definitely say, because this L1 is smaller than this R2, hence it is. But if you carefully observe, this 6, which is L2, is not smaller than this R1, right? So I cannot say that this 2, 3, 6 is entirely smaller than this 4, 7, 10, 12. But what I wanted is this L2 to be lesser than equal to R1. This is what I wanted, but this is not the case. So if I write the numbers, it is like 6 lesser than equal to 4. So can I say, in order to make this condition true, I have to reduce 6. I have to reduce 6, correct? And I have to increase this 4. So increasing 4 means I have to take this 4, so it will go over here, and the right half will be 7, 10, 12 now. Hence the R1 will now become 7. And if I take 3 elements from the first guy, I'll have to take this 6 and I'll have to push it over here. So do you get an intuition that in order to decrease 6, I have to take it out? And if I'm taking it out, I'm actually adding numbers from the first. That means I'm picking more numbers from the first. Hence you get an intuition. If we are saying that it is not satisfying the condition and you need to take numbers out, or you need to add numbers. If you need to add numbers in the first, you move in the rightward direction. You want to go on the rightward direction. Let's take another example and understand, when do you want to come to the leftward direction? Over here you have understood that you want to add more, or you want to take more numbers from the first. Now let's assume you have taken 4 elements. Yes, you have taken 4 elements from the first array and the remaining 1 element from the second array. Now, if this is L1 and this is R2, can I say that L1 has to be lesser than R2 in order to this be a valid one? But I see that 7 is not lesser than 3. It is not. So I have to reduce 7. So if I want to reduce 7, I have to take this 7 off, which means I have to move in the leftward direction. And if you take this 7 off, it will go over here, correct? And that means you're taking 3 elements from the first, you're reducing numbers in the first. Hence, you'll have to add numbers. You have to take more from the second. Hence, this will go. So automatically, if you want to reduce numbers, you have to come to the left. You have to pick lesser numbers from array 1. So I hope you have understood at what portion you have to move to the right and at what portion you have to move to the left. And this is similar to binary search. You either search on the right half or either you search on the left half. Correct? That is what you do. So over here, our binary search will be done over something like how many elements are you wanting to pick from this array, first array. That is what we are going to do the binary search on. So I hope you have understood the intuition of binary search. Now once I dry run the algorithm will get super duper clear. So let's do the dry run on the algorithm. Okay, so let's take this example. Now always remember, we will do the binary search, or we will always take the first array to be the smaller array so that the complexity is reduced. The binary search takes place in a smaller space. Now if I ask you a very simple question, you know one thing, the left half will be having 5 elements, right? Very simple question. What is the minimum number of elements that you can pick from this array 1? It'll be like 0. 0 is the minimum number of elements that I can pick from the first. What is the maximum number of elements you can pick from the first array? It'll be like 4. I can at max pick a 4 element. So in binary search, there is a low, there is a high. So make them low and high. Okay. And assume imaginary index, like this is our partition index 0, 1, 2, 3, 4. These are partition index. Okay. Now, what is the valid condition whenever you took a left half and right half? If you remember, the valid condition was this: L1 should be lesser than R2, L2 should be lesser than R1. So just write the valid condition. Okay. So let's write the valid one. Now let's start. So what is the middle? So assume the middle is called as cut 1. That's 0 plus 4 by 2, which makes it 2. So what I'm saying is, why don't I try picking up couple of elements from the left half? Why don't I try picking up couple of elements from the left half? I'll be like, okay, let's pick couple of elements from that. And I need a total of 5 elements. So I'll be like, okay, why don't I pick the rest 3 elements from the second array? So the rest 3 elements are picked from the second array. So if I write them down, it'll be something like 7, 12, 1, 2, 3. That is what the left half will be. And the right half will be 14, 15, 4, 9, 11. Now, what do you see over here? Is this a valid left half? You'll be like, no. Why? Because this 12 is not lesser than this 4. Hence, you need to move leftward. For sure, you need to move leftward. Now, whenever you need to move leftward in binary search, what does that mean? Leftward movement means deleting the right space. Deleting the right space, does it mean something like this? Yes, it does. Yes, it does. So I'm going to move to the left, which means high will become mid minus 1. So mid is 2. That is cut 1. High will become 1. So why don't you move on the left? So let's move and try. So currently low is at 0 and high is at 1. So what will be the middle? The cut 1 will be 0 plus 1 by 2, which is 0. So what I'm saying is, why don't you try to pick 0 elements? Yes. So if you're picking 0 elements from the array 1, how many elements will you pick from the second array? The remaining 5 have to be picked. So you're going to pick the remaining 5. That means these elements. So if you're not picking anything from here, which means nothing from the first and everything from the 5 elements from the second, and over here it is going to be 7, 12, 14, 15, right? And over here it will just be an 11. Now, are these all elements smaller than this? You see that 9 is not lesser than 7. Hence, you have to remove this 9 and you have to add it over here. Like you have to add some elements over on the first so that you can remove this. Hence, you have to move right. And in binary search, when you move right, what does that signify? Low equal to mid plus 1 is what it signifies. And if it signifies that, what can you do actually? You can just make low as mid plus 1, hence low will become 1. Correct? So let's do the binary search for this. So currently low is at 1, high is at 1. Okay. So assume the middle, which is cut 1, is 1 plus 1 by 2. That's 1. So you're trying to take one element from the array 1. Right? So from array 2, how many elements will you take? 4. That are the remaining elements. So the left half will be like 7. Over here it will be like 1, 2, 3, 4, because cut 2 is over here. So I'll take all the 4 elements. The right will look something like this: 12, 14, 15. Over here it will be something like 9, 11. So can I say this 7 is smaller than this 9? This 4 is smaller than this 12, which means this entire half is smaller than this entire half. Hence, the validity condition is proved. Hence, I can say that this is a valid left half. And if this is a valid left half, which will be my kth largest or kth element? Either 7 or 4, which is the maximum 7. So I can say kth element over here will be 7, which will be my answer. So I hope you have understood why I did a binary search in the smaller array, because the search space will be small. Hence, I'll be requiring a complexity of log base 2 minimum of n comma m, assuming n to be the length of the first array, m to be the length of the second array. You do a binary search on the minimum length array. Now, is it over? No. There are some edge cases that I need to discuss. After that, we can move on to the code. So the couple of edge cases are, let's assume I give you something like k equal to 3. Okay. And now I ask you, what is the minimum elements that you can pick up from array 1? You'll be like, it is still 0. I'm going to pick 0 elements from the first and the rest 3 from the second. Now if I ask you, what are the maximum elements that you can pick up from high? Is it 4? Is it 4? No, it's actually 3. So this is one of the edge cases. If k is actually smaller than this size only, you cannot pick up 4 elements. That's practically not possible. So we're not going to pick up 4 elements. Correct? Now, other edge case. What if k is something like 7 over here? K is something like 7. So what you know is, at maximum, from the first array, you can pick up all 4 elements. But what will be the minimum element that you can pick up from the first array? Will it be 0? Now let's assume you take it as 0. If you take it as 0, how many elements are there in the second guy? That is 6. But you require actually 7. So this is one of more edge case. If this k is greater than your length of the second guy, then this low will be 1. In minimum, you have to pick 1 guy from the first. That is, otherwise you'll not be able to complete 6 guys. So you have to be very careful when you're assigning low and highs. I'll show you in the code, but you have to be very careful. Now this is okay. Now what if? There were a couple of things like L1, L2, R1, R2. Now, if you are doing a cut over here, correct? So this was your L1. So can I say if the cut is done at the second, L1 is array of 1 of cut 1 minus 1. Can I say this? Yes. And can I say if the cut is, let's say, done at the third index of the cut 2, this will be L2. So can I similarly say it will be array of 2 of cut 2 minus 1, correct? Or it will be R1. Can I say R1 is nothing but this, which is the second index itself. So array of 1 of cut 1. Similarly over here, it will be array of 2 cut 2. Now, if you're doing a cut over here, do you have anything? Hence, you don't have any element. If cut 1 is 0, please make sure you make this as int mean, because you don't have anything on the left. Similarly, L2 as int mean. What if you're doing a cut here? Then you do not have anything. You do not have any R1 on the right. So please make sure you do it as int max. And this guy also as int max. So that while comparing the validity check of this doesn't fails. Right? Please make sure you make it as int mean and int max. So these are the edge cases you need to take care while coding. Apart from this, it's much similar to the previous question. I'll be discussing the C++ code. Again, the Java code is exactly identical. Just in case of int mean, you have taken an integer.minimum value and integer.maximum value. Otherwise, it's exactly the identical code. So as you can see, you're given array 1, array 2, n, m and k. So please make sure that you check if n is greater than m. Just do the reverse so that you always do the binary search on the smallest one. So assuming that we are currently on the smallest, please assign low. Either it will be 0 or k minus m. Assuming that in minimum you have to take something from array 1. That is what I've written. And high will be min of k comma n. Assuming again that you cannot take all the elements from array 1. That is what I've written. I've explained this edge case. After that, you do a simple binary search from low to high, and then cut 1 will be middle, which is low plus high by 2. I'm writing it in right shift of 1 because bit operations are faster. After that, I have a cut 2, which is the remaining elements, and then I have take L1, L2, R1, R2 as I said. Now I know the valid condition is very simple. This is the valid condition. If it's a valid condition, I know the kth element is maximum of L1 and L2, so I return. Now if it is not a valid condition and I see that L1 is greater than R2, I know that I have to reduce elements. And in order to reduce elements, because L1 is greater, I need to make it smaller. I have to reduce. If I have to reduce, I have to move a high to the left. And if it is not, it's the other way around. Then I have to increase elements. So I have to move to the right, which is cut 1 plus 1. And this will definitely be executed if there is the kth, like if the arrays are sorted. If the arrays are not sorted, then only you'll come to line number 35. And then that means the test cases are wrong. This will never be executed, but you have to write it because the function requires a return statement. That is why I've written it. I hope you have understood the entire explanation, intuition and the code. Just in case you did, please make sure you like this video and drop a comment below. If you're new to our channel, do consider subscribing with this. Let's wrap up this video. Bye bye, take care.
Don't ever forget your golden